Okay, thank you for this kind invitation. This is a slightly different subject. Oops, it was a different subject. Okay, so the backdrop of this talk is gravitational wave astronomy in the millihertz regime, in the millihertz range, and this is a range of frequency where almost all the sources we can think about are expected to be very numerous and very powerful. The science case for this astronomy has been growing over the year, and it's so important that ESA recently decided to devote its third large mission in the so-called cosmic vision planning to a gravitational wave observatory, to a spaceborne gravitational wave observatory in the millihertz regime. As you know, the background of this is a mission that has been studied for a couple of decades, both by NASA and ESA, jointly and separately, which is called LISA. It's a spaceborne interferometer with 3 arms. And, the way this detector works, I hope you don't feel insulted by the simple explanation, but the way this detector works is that if you measure the time interval, the space-time interval between 2 wave crests in a beam that you send from an emitting free-falling spacecraft to a receiving free-falling spacecraft, you obviously see constant frequency. If there is an intervening gravitational wave, if you have an intervening gravitational wave, if you still use the wavefront as your reference frame, you see the 2 local free-falling inertial frame like they were accelerating one relative to the other. And you can do the calculation right, and you get that the derivative of the frequency relative to the proper time of the observer is directly related to curvature. So these are tricks that measure curvature, intervening curvature integrated over the beam. Unfortunately, you get the identical effect if your reference frame is standing still and you're accelerating relative to the local inertial frame. So if any force pushes your test particle, your receiver satellite out of their free-falling frame, you see an effect. So in this sense, these detectors are differential dynamometer, though they are time-delay differential dynamometer. So, and a gravitational wave compete with forces. And unfortunately, satellites are accelerating in space. Mostly they are disturbed by solar radiation pressure. So these accelerations are much larger than the one corresponding to the tidal acceleration of the gravitational wave. And so you have to correct for the acceleration of the spacecraft and use another body as an inertial reference. And the trick that had been devised many years ago is that you carry inside the spacecraft a free-falling test mass and you follow the test mass with your spacecraft. So you measure the acceleration of the spacecraft relative to the test mass, correct the signal, and this is like doing the tracking from one test mass to the other one directly, and the spacecraft doesn't intervene anymore. In reality, in the LISA design, for instance, you do this twice. You have 2 back and forth links that are phase locked like a transponder in a spacecraft, and that's the equivalent of reflecting the light that you cannot do at 1,000,000 kilometer distance. So in LISA, the configuration was 3 of those arms, 5 million kilometers apart, and so you measure the tidal acceleration of pair or test masses. You have to be free-falling to a very high quality. You're talking a fraction of a femto G. You have to measure picometer, and you have really to have those test mass falling free. This concept has evolved into a smaller and probably less expensive concept that was studied by ESA for this as a base for this new observatory, which was called NGO and is now called eLISA. But now it's clear that while we are starting study the final mission, that this is the parameter space where you can try to play tricks to maximize your sensitivity while remaining within a cost envelope that ESA has devoted to such a large mission. So the basic tricks of a mission like LISA, one is the orbit. This spacecraft, this triangle of spacecraft, in reality, there is no need to push those spacecraft. This is a solution in celestial mechanics. Each spacecraft follows an elliptic orbit, but they are tilted and phase shifted, so they form a triangle that goes around the sun, which is very important because it's like opening a synthetic aperture telescope, so you can point the source of the gravitational wave. The second trick is this idea of non-contacting spacecraft, where you don't touch this test mass, which is your inertial reference, and you do that by measuring where the test mass inside the spacecraft and feeding back this information to a set of little rockets that push the spacecraft back and forth to keep it centered on the test mass. So if you go into a bit more detail, the basic instrument in LISA is a test mass, which is surrounded by a lot of accessories, including a vacuum can to handle vacuum on ground, an optical bench to do all your interferometry, both the local one to measure where the test mass is and the one to the distant spacecraft, and a telescope to exchange the light with the distant spacecraft. Oops, sorry. This is the test mass. This is the LISA Pathfinder test mass, of which I'm going to talk later. It's a 2-kilo gold platinum object. The spacecraft follows it in one direction. Unfortunately, it cannot follow in all directions. So in other direction, not aligned with the laser beam, you push the test mass gently with electrostatic forces, and that's why it's all surrounded by electrode. But there is no contact. There are millimeters all around this test mass when you're in flight. The spectroscopy is done, the interferometer is done on an optical bench. This high stability hydroxy bonding technique where you put together optical component. This is zero-dur. You put together optical component together with this bonding technique, and the result is like you had carved everything out of the bulk. The mechanical properties and the dissipation properties are the same, and this is the optical bench of LISA Pathfinder. So this mission, the reason why there is so much interest in this mission is that this is a mission which is a mission in fundamental physics, because most of the observations are in the strong gravitational regime. And so they probe things like the accuracy of the Kerr metric in describing a black hole, the existence of the event horizon, and so on. But it's also a mission in cosmology, because you can trace binary of supermassive black holes since the beginning of the universe and so on. So you see different sources, and these are just the expected one that goes down to galactic binaries, of which you will see you can do. I have no time to go into the science. This is mostly a talk on LISA Pathfinder, but just to give you an idea, a binary merger of two supermassive black holes, like the one that are in the center of galaxies, after a collision of two galaxies is expected to be a signal that with a redshift of 5, this is the signal in the data with no data processing, right? So contrary to having to do very sophisticated data processing technique, this really sticks out of the noise, and signal-to-noise ratio here, we are talking about 1,000. This is the numerical calculation of the merger of two black holes into a single black hole. So signal-to-noise ratio for close objects are above 1,000, but they maintain significant signal-to-noise ratio up to redshift of 20. So this will be the deepest probe probably available to see the universe, and the signal-to-noise ratio is so high that you measure the parameters of those sources like spin alignment, all that, and this is independent of any model because it's just purely from the gravitational field. And if you go on the other extreme of the sources, you have this binaries of compact objects in our galaxies, like a binary of white dwarfs or a neutron star. And it's a fantastic astronomical census, because you can see binaries that you cannot see electromagnetically, you can hear, you would say. But also there are a few binaries of which we know everything, and we can calculate the signal without ambiguity, and LISA has to see that unless it's broken, right? So this is what we call verification binary. So there is no uncertainty on the fact that LISA is going to detect the signals, though maybe not the most interesting one. Now, can you do this mission? Can you test on ground? Well, now I'll tell you about LISA Pathfinder and how can you test that this mission works before launching a mission which is likely to be around 1.2 billion, whatever you think, euros or dollars, doesn't make much difference. As I said, so let me bring you through the disturbances in a detector like this one. The first one I told you is the fact that if somebody shakes this test mass, it looks like there were gravitational waves, right? And real forces shake the test mass relative to the local inertial frame. That's what it matters. So it's a local phenomenon. You don't need a 3 spacecraft to see that. That's a phenomenon inside the single spacecraft due to all sorts of disturbances. The second phenomenon is that you are supposed to measure the acceleration of the test mass relative to the laser wavefront. But in reality, you end in measuring the acceleration of the test mass relative to the optical bench, and then to the optical bench relative to the telescope, and so on. So you can make many errors due to misalignment. We call this the reference frame noise. This is local. It has nothing to do with the distant spacecraft. It's a chat between, it's an interaction between the spacecraft and the wavefront. And so, again, it's local. Then, obviously, when you measure things, you do electronic noise, and so you will have noise from electronics, and again, this is local. The only source of noise which is non-local in an interferometer, that's the same on ground, is that laser stability, laser frequency stability is much worse than what you need for gravitational wave detector. The phase shift due to fluctuation in the laser are much larger. And so what you do on ground is that you always compare the light that has been emitted at the same time. So any difference in the frequency between the light is due to something intervening in the propagation of light. In space, you don't have the luxury of having equal arms, so you have to reconstruct that by sending the light on 2 opposite paths and recombining the light, and you do this in software. You need very good phase meter, but it's everything you can demonstrate on ground. It has been demonstrated in a couple of laboratories. And so the situation with the noise in LISA is that everything is local except for this little contribution. Forced noise at low frequency, reference frame noise and interferometer noise at high frequency, and unfortunately the big deal at low frequency cannot be tested on ground, because on ground there is 1G and you cannot free fall test masses. And that's the idea behind LISA Pathfinder, which is going to fly this year, and that's maybe the reason for this talk. So LISA Pathfinder is conceived as being a test of the entire local instrument for LISA. So demonstrating 95% of the total error budget that matters. Do this with the hardware that you can fly on LISA eventually without many changes, and then do a consolidation of our physical model of all the disturbances that prevent pure Einstein geodesic motion in space. And if you look at the performance we're requiring, these are, you can read this as newtons. LISA needs 10 to the minus 15 Newton. For limitation due to the kind of tests we do, we aim at being there by factor 10. And by the way, this is a factor 1,000 better than any mission that has flown so far that uses free-falling test masses. So that's the reason why you need a dedicated demonstrator, because the gap with what has been done up to now is pretty large. So the idea of LISA Pathfinder is don't bother about the 5 million kilometer, everything is local. So you take a test mass as a reference, as an inertial reference, and look at the acceleration of another test mass relative to the other one, and show that you can stay so still as is needed by LISA. And so basically, it's one full LISA arm squeezed into one single spacecraft, half a meter size. So the complement we fly is 2 of these gold-platinum test masses that are free-floating inside the box. An interferometer sitting on an optical bench. There you have to carry a lot of accessories. This is the motor to lock the test mass during launch, otherwise it breaks the spacecraft because it's free and it's not contacting. You see here UV light that has to discharge this test mass that keeps charging with cosmic rays. And there are many other little tricks you have to play. You play this trick of following one test mass with the spacecraft. Unfortunately, the other test mass you cannot follow. You cannot follow 2 test masses along the same direction. And so you apply a little electric field, trying to be as quiet as possible, and this is the limit of the test. So once you have assembled everything, you put this into a spacecraft which is dedicated. You use a propulsion module because we have to go into an interplanetary orbit. A low Earth orbit is too noisy to do a significant test of this technology. So this is the optical bench. This has been delivered now 2 years ago. That's the flight model. It's optomechanics, and because of this reference frame things, you have to measure and do things at the micron level. And so this, because it's optics, it's basically optics, you have to be very clean. And so all the integration and so on is a class 100 kind of technology. The test mass is a gold platinum, very non-magnetic, very homogeneous, very pure, very everything, very expensive. This is the box that carries the electrodes, gold-coated molybdenum on sapphire, beautiful, expensive. And this is when it's been inserted into this vacuum enclosure that you have seen. So the test mass is inside this hole. The laser beam goes through this hole. You see again here, despite this is masses and piece of metal, you have to do class standard integration because it's optical, and you do coordinate machine alignment. I know it looks like a movie of the 30s, but you have to do all under coordinate machine and align everything. The overall alignment quality is something like 10 micron over half a meter. Yeah, you see here, probably you see the electrode housing. The test mass goes inside here. This is the test mass that gets integrated and so on. I think in the interest of time, I will speed up a little bit. Then the two sensors have been, so the sensor have been delivered at the end of last year. The two inertial sensors with the two test masses basically are integrated with the optical bench in a structure which is all glass. So this heavy thing is all kept together by glass despite the shaking that we undergo, and everything is linked to the spacecraft through the struts. Here you see a detail of the light goes here on the optical bench and then enters into this hole. I find this picture very moving for me. And then, I mean, the integration proceeds. I don't think I have the time. Everything is in this central cylinder. You see this during vibration test. So this glass things has costed so many millions. You vibrate like hell to see if it stays together during launch. So the instrument goes here, and around there is all the electronics, and this is the spacecraft with the propulsion module, and here you see the final integration of the payload in the spacecraft that happened roughly a month ago, a bit less than a month ago. So this is the instrument is closed in this box, and there is the very emotional moment on where the instrument, after 8 years or 10 years of development, gets inserted into the spacecraft. If you're patient a second, it will go into the spacecraft. And now the situation is that the payload is integrated in the spacecraft. Here we go. Yeah, micron alignments. The payload is integrated in the spacecraft. This is a picture. This is a picture I took myself at the prime contractor premises. You see here the little rocket that I used to center the spacecraft relative to the test mass. Are we going to get to the performance? How do we know? I mean, we need 0G. I can tell you a little bit of what we did on ground to prepare. Obviously, we maintain an error budget. Francis would know that in this field you maintain these huge error budgets, right? And we could test the interferometry end-to-end, substituting the test masses with mirrors. We did this during one of these tests of the spacecraft, where the spacecraft is put in a big box that imitates free space. There is no hair, and there are powerful lamps that gives energy to the solar panel, so that the spacecraft is autonomous and takes the energy from the solar panel. We tested the interferometry, and we got the requirement, despite this environment is much harsher than what we expect to have on ground. So this is picometer per root hertz quality interferometry. To test against Paraxidis force, we cannot do in 0G, but we can do something. We can test against forces acting on a surface, because we can imitate the test mass, making it hollow and hang from a torsion pendulum, then surround with this box that is also the shield, but is also the source of all the disturbances. And over the year, we could demonstrate that the surface forces in 1 degree of freedom this is just the limit of the instrument sensitivity, are just close. There are no unforeseen excess forces at the limit of the requirement of LISA Pathfinder. We tested many different phenomena: thermal effect, collision of thermal molecules, Brownian noise due to damping from the residual gas. We're talking 10 to minus 5 Pascal here, where we also discovered a few things. I have no time. Charge patches. This is a terrible word in the field of fundamental physics. What we could measure the charge patches, find and demonstrate that they are not they are not a problem for the error budget. So from what we know now, though our specification here, this is a relative acceleration, this is frequency, our specification are just those one, we should be able to get very close to what LISA requires, except at the lower frequency because of this, the need of applying this electrostatic force to control the second test mass. So the experiment in space is more or less what we did in the laboratory with the torsion pendulum and other things. We go there and we want to assess what are not just saying, okay, got the requirement, let's go home. We want to assess where the noise is coming from. So we want to assess who are the leading item composing the noise, consolidate our understanding on how they depend on the parameters of the environment, measure some critical parameter for which we have spent a lot of money. I will give you an example on gravitational balancing and so on. And then finally return an upper limit and say, well, LISA is not going to be worse than that, right? And this is our objective. So for the people that follow a gravitational wave detector presentation, we want to end with spelling out the noise in its proven and tested components. We carry a lot of monitors to be able to correlate disturbances with the acceleration of the test masses, and I think I will skip one example. I mean, at least for one parameter estimation, we need to, despite we are in 0G, this 0G in reality is something like 5 nanoG because of gravity generated on board the satellite. We compensate for this 5 nanoG because they are too much by putting a heavy and specially designed mass close to the test masses. And we do that by recording every single piece of equipment. We weight it, we measure where it is, we calculate the gravitational field, and from that we calculate the test mass. And we have a chance to test this in flight by letting the test mass fly free for 200 seconds and measuring the acceleration of the test mass in absence of electric field. I don't have detail, but just to tell you what kind of experiment we're going to do on flight. A minute on how we operate this thing. Usually in space mission, you have a mission operation center and a science operation center where the mission scientists sit. Exceptionally for this mission, the scientists sit in the science operations center, and the reason for that is that we have to do a 24/7 attendance of the mission where we analyze the data that come in real time and we replan the experiment as you do during a debugging of a complicated experimental apparatus. So we need roughly 30 people for a few months. We have collected more than 50 people from 11 institutions worldwide, including NASA. This is a scheme of a few days of operation where every few hours you do a different experiment. You test the charge, the acceleration, the temperature, and so on. We have tested this scheme of operation we have done many simulations of the mission with an end-to-end simulator, including a simulator where also the hardware is activated. You see us you see the scientists taking the data during we launch in November. We have a launch slot between November 15 and November 30. We launch with a Vega rocket, which is an Ariane Space fabricated in Italy. We fly for roughly 2.5 months, and then we have a 3 months initial operation phase. And so at the end of the 3 months, we should be able to deliver to ESA the first consolidated data about geodesic motion in this orbit, which comes very handy because to do the L3 mission, ESA has formed an advisory team, and this advisory team, together with ESA, has now devised a development stage where as soon as the data of Pathfinder come, which is mid-2016, the call for the L3 mission and the start of the study of the mission starts. So there will be basically no discontinuity between LISA Pathfinder and the implementation of L3, eLISA, or whatever you call. So the most likely date to launch, or one of the most likely dates, is November 25, that I find very telling, because it's the date of the fourth of the papers of Albert Einstein on general relativity. So this is our way of celebrating 100-year general relativity. Thank you. One down there? Yes, shout.
How many times it is planned to correct the satellite? Because as far as I know, the satellite, when you want to correct the orbit, or you want at least to move it for 1 meter, then this is a propulsion system, this is a vibration, this is, thousands of things, and that will affect not only the optics, but your test mass. And are you going to use the same caging system at that point, or no?
How many questions? You're alluding to LISA, not LISA Pathfinder. LISA Pathfinder, we are doing station keeping every week, roughly. But a week is plenty for the experiment we have to do locally. We don't observe gravitational wave, right? So we don't need long observation time. In LISA, there will be maneuvers, not one-day maneuvers, but a few hours maneuvers, mostly to orient the antenna, at least according to our conventional wisdom on LISA. In no case we recage. We never recage. These maneuvers are very gentle. We are talking meter per second authority in the maneuvers, and we never recage. Actually, in LISA, we never even increase the control force. We stay, but the data will be noisy. So you'll have a gap in the data, and this will be every 10 days, roughly.